So, shapes, huh? We're diving deep into the world of Platonic solids today. You know those geometric figures like tetrahedrons, cubes, octahedrons? They've fascinated mathematicians and philosophers for ages, even way back with Plato in the Republic. But we're going beyond just the abstract math this time.
What's really neat here is that this deep dives using a surprisingly intuitive approach. It's called close-packed spheres.
Close packed spheres. Okay, now you're going to have to break that down for me.
Absolutely. Think of like marbles all packed together as tight as they can possibly be. It's almost like, well, instead of trying to fit puzzle pieces together, we're looking at what kind of structures just naturally show up from that simple arrangement of spheres.
Okay, so we're using these spheres as our building blocks, and from there we can start to see how these famous Platonic solids appear.
Exactly. Much surprised you to learn that all 5 Platonic solids can be formed this way.
All 5. Well, the first few, like the tetrahedron, the cube, octahedron, yeah, I can kind of picture those. You see them everywhere in nature, don't you?
Yeah, exactly. Picture like when you see oranges stacked up in a pyramid at the store. That's your tetrahedron. Or salt, the way its atoms are arranged in that repeating cube pattern. These shapes are everywhere, even influence the architecture we see every day. That cube especially, with its clean, simple structure, it's been like a foundation in how we understand space and geometry for, well, forever, basically.
Okay, yeah, I'm with you so far. But the source material we're looking at takes it even further, right? It says even those really complex ones, the icosahedron, that's the one with 20 triangular faces, and the dodecahedron, the one with 12 pentagonal faces, even those can be made with our sphere packing.
That's where things get really interesting. Most people hit a wall trying to visualize something that complex just appearing out of a bunch of spheres.
I can imagine. For a long time, people didn't even think it was possible, right? Our source mentioned this assumption that Platonic solids, they need these perfect uniform lattices in their faces, kind of like, a perfectly tiled floor. But to get an icosahedron in this close packed sphere world, gotta toss that assumption out the window.
You got it. Source makes a key point here. To form icosahedrons with sphere packing, you actually need 2 different types of lattices in their structure.
Yeah,
That's how this intricate shape can even exist this way.
2 different lattice types. Huh. So it's not as symmetrical as, I don't know, maybe we tend to think. Does that mean these complex shapes are inherently less perfect than the simpler ones since they don't have those perfectly uniform structures?
That's a great question. Gets right to why this whole close-packed spheres thing is so groundbreaking, I think. It makes us rethink what perfection even means when it comes to geometry. Instead of everything needing to be rigid and uniform, we see that complexity, even elegance, can come from putting simple things together in unexpected ways.
Okay, I think I see where you're going with this. So how does this all connect to the dodecahedron then? That's the one with the pentagonal faces, right? Because honestly, that one still feels like a magic trick to me. Spheres or no
Well,
spheres.
this is where duality comes in. Duality in geometry, it's like 2 sides of the same coin. Yeah. So for every polyhedron, like our icosahedron, there's a matching, like a dual polyhedron. And in this case, it's the dodecahedron. They're totally linked, almost like dance partners or something.
A dance between shapes.
I like that. Okay, so how does this dance work when we're talking about close-packed spheres?
In a really fascinating way. So picture this. In our close pack setup, the vertices, those points where the spheres touch, right? The vertices of nested icosahedrons, they actually mark out the centers of the dodecahedron's faces.
Whoa, okay, now my brain's bending a little. So you're saying those complex shapes, they're kind of like encoded within the simpler ones? Like the dodecahedron's just hiding in plain sight inside that icosahedron pattern.
Exactly. And this hidden dodecahedron, it has some unique quirks. For one, it doesn't have a homogeneous lattice, meaning the spheres within its pentagonal faces, they aren't arranged uniformly. Plus, it has 2 different kinds of vertices, so even more complexity. It's like we found this secret code, and the key to cracking it was just packing spheres together the whole time. Who knew something so simple could lead to something so, I don't know, intricate?
And get this, it's not just theory. This duality thing, we see it in nature too. There's this thing called the holmium magnesium zinc quasi-crystal.
Quasi-crystal, that even sounds cool. What's the deal with that?
This material, it actually forms a dodecahedron with those perfect pentagonal faces, just like in our sphere packing model. That discovery was huge in material science. It suggests that we could actually engineer new materials, ones with crazy properties we haven't even seen, just by copying these natural geometric arrangements.
Hold on, so we're talking about potentially making brand new materials all based on the shapes we're seeing pop up from these little spheres.
Exactly. And this is just one example. Imagine the possibilities if we just keep going with this close-packed sphere idea. What if we change up the sphere sizes? Or, like, introduce different forces? Who knows what other patterns we might find hidden in this system that seemed so basic at first?
This is wild. We started with just packing spheres together, and now we're talking about hidden codes and new materials and like the secrets of the universe. It's like, I don't know, a whole different way of looking at geometry than what we're used to.
It really makes you wonder what else we might be missing,
Yeah.
By just focusing on those traditional rigid shapes, this close-packed sphere approach, it's like it's showing us a deeper geometry, something more fundamental, where complexity doesn't need to be complicated, it just emerges.
It's like we've had all the puzzle pieces this whole time, but we never thought to put them together this way before. And look what we find when we do.
Exactly. And the most exciting part is we're just getting started.
Mm.
If we keep messing around with this, changing the spheres, adding in new things, who knows what other hidden patterns are waiting to be discovered, right?
So it's not just about understanding these shapes, like in their own little world. It's about taking that knowledge and maybe discovering something totally new, something that could change things in the real world.
That's it. This deep dive, it's shown us these aren't just, math class doodles. They're the actual building blocks of things. And that's something you can really grab onto.
Mhm.
The possibilities are huge. It's really pretty exciting.